room. All right, so today, a lot of stuff to cover today. There's a midterm next week, right? Thursday night, not during class time, it's in the evening. There's details online and you'll get emails about more things about that. And next lecture, so lecture on 2 days from now, Thursday will be mostly about a review. I'll review what sort of material is going to be on the midterm. I'll talk about how the midterm will be graded. I'll talk about what you should do to maximize your, score and do as well as you can. I'll just say right on the bottom line, we'll give you more details next time. The main goal you got on the midterm next week is to convince the graders. There'll be a different grader for each problem. They're all in witness protection. You will not find out who they are. But your goal is to convince the graders that you know what you're talking about. That is your main goal. It doesn't matter even if you get the wrong numerical answers. In a lot of cases, you can still wind up getting full credit on a problem. I'll give more details. That's not a guarantee, but it sort of depends on what mistake you make. It's all about partial credit, though. The way you get credit in a physics class in general, this class in particular, is by demonstrating your knowledge as you solve the problem. That's why in class, you write stuff out and try to justify my steps and label stuff. I don't do as good a job on the board as you should do on your test, though, in terms of including all your steps and making it clear. I'll try to speak through it. Anyway, we'll talk about that next time. And also talk about what's on the midterm. So I'll tell you right now, it's chapters 1 through 7. We're covering stuff today that bleeds into the following midterm, but don't run out. Because you're going to need to know this stuff. This class goes really fast. The second midterm is only like a month away. It's coming fast. So it's worth keeping up with what's happening. Anyway, all right, so we'll do midterm review mostly on Thursday's lecture. Maybe I'll blend in some other stuff depending on how far we get today. I'm going to cover a lot of material today. I'm covering chapter 9 today. We skipped chapter 8. It's possible I forgot to mention that in the last lecture. So those of you who read chapter 8, that's great. It makes you a better person, happier, more satisfied in life. It'll actually benefit you in this class, potentially, but we're not going to explicitly test you on that exact material about gravity. It actually will help you out in AD, too. Gravity turns out very similar to E&M in some respects, whenever R squared force law. Today we're talking about systems of particles. In particular, we're going to talk about a new conservation law. I'll put it down here, though. Conservation of momentum. We already introduced the notion of momentum. Today we're going to see why it's useful. So this is a different idea than conservation of energy. It's a separate conservation law, but you might think, well, what do I need that for? I've already got conservation of energy. Once I've got one, it's not enough. For some problems, it's enough. For some problems, it's not. We'll see how far we get. We might do this next lecture as one of the things that I carry over, but I'll try to get to the ballistic pendulum today, which just means measure the muzzle velocity of a bullet coming out of a gun. How do you do that? How did frontiersmen do it? They didn't have radar and all this, right? Well, they did it using conservation of momentum and conservation of energy used in a smart way. And we'll work through that. You need to use both, though. It doesn't enough just to have conservation of energy. You need conservation of momentum as well. Center of mass, very important concept. Now sort of lead us up to conservation of momentum. And I'm also going to introduce the notion of impulse. Impulse is analogous to work when it comes to momentum. I'll say it like an SAT. Impulse is to momentum what work is to energy. All right. So when you have conservation law, things aren't always strictly conserved. You might have a little term on the right hand side of final minus initial. This is the thing that will show up on the right from the end. All right. Super. Okay, good. So let's get started. Center of mass. So what is center of mass? First I'll give you the definition for it, and we'll think about what it's useful for. If you want to know where the center of mass of a system of particles is, you'd say, well, let's take an average of the locations of all the particles, a weighted average. In fact, this is the canonical example of a weighted average. You're averaging by the masses of those particles, and center of mass doesn't tell you about its weight. It tells you about its location. So we better get something out that's got meters, right? So the center of mass, you're all right. So there's a bit of a risk here with me writing it this way. COM, you might think means center of mass, but it could also mean conservation of momentum. So what I mean here is center of mass. So what is the center of mass? It is, so we'll say R center of mass, some location, a vector in space, right? Well, it just equals the sum over all n of the particles in my system. So how many are not familiar with my capital sigma summation sign? Only one of you is not familiar. All right, so it's a couple. Anyway, all this means is everything to the right, sum it up, and have the index I, as I've written in here, step from 1 to n. So there's going to be something written right here that gets copied n times, they get added together. That's all I mean by it. So what am I adding up? I'm adding up the locations, R sub I, each R is a vector in general, right? I'm adding up each location of each of my n objects times their mass, right? And so this thing has the wrong units for a location. That's meters times kilograms. I have to divide by something. What I'll divide by is the total mass. What do I mean by the total mass? I mean the sum of all the masses. So formally, I'd say, I just take the sum from 1 to n of m sub I. That's all I mean by the total mass. Right? Great. Very powerful idea. So I've written this thing right now as if there are n discrete pieces. Like I've got n balls, or n, I have 3 pieces of chalk, and I want to know where the center of mass is for that system of 3 chalk. In that case, capital M would be 3. And then get 1, 2, 3, but the 3 I add them up. The locations times their mass and divide by the mass of all 3 pieces of chalk. I could also have a continuous distribution, right? I could have like my body. So I want to know where the center of mass of my body is, right? Well, that requires an integral. So I have to add up all these little infinitesimal parts of the funny shape of my body, right, to find out what the center of mass is. And it's kind of surprising what the center of mass can be for our bodies, right, for a person's body. We'll talk about that in a few minutes too. And it turns out that's useful for athletes and for dancers, right? They can do tricks as a result of the fact they have to follow the same laws as the rest of us, laws of physics, but they can make their bodies look like they're doing things that defy laws of gravity and other things. How they do it? Well, they do it by manipulating the center of mass in clever ways, by bending the body. Sort of obvious idea, but it's surprising when you see someone who's good at it. It's surprising what it looks like. Okay, great. So center of mass, very useful concept. If we think about Newton's second law, I mean, you'd like to know about Newton's second law applied to a system. We already talked about how we can apply it to a system. One way to do that is to sum up the individual. Let's see. Let's write it out. So for one object, what is it? It's F net for some object I. Right. This is for one particular guy. Is equal to mass of that object times the acceleration of that object. Right. Very good. You know that. Well, there's a couple ways to think about what happens when you have lots of particles around. One thing is that we could take the sum on both sides. So let's sum up all the forces on one side. What do we get? We could have total net. So this is a vector still in general. You can just do the x component, but I'm writing it as a vector. I say, okay, what is the total? Oh, I already told you. To get the total mass, we have summed up the masses. To get the total force, we'll just sum up the net forces on all n of our objects. So if you like, there's 2 sums here. There's a sum for each object of all the forces acting on that object to get the net force on the object, right? But then there's also the sum across the n different parts, the n different objects, right? So I equals 1 to n of, for object I want its force and I want its net force. So there's 2 sums. There's a sum to get the net. There's a sum to get the total. What does it equal? Well, I can just follow this, right? I just take this and sum it over all I equals 1 n. Anyway, this gets tedious with lots of algebra, so I'll skip to the chase. And the book does this if you want to see the intermediate steps. But if you then carry this out and say, well, what is a? Well, that's just, remember, a sub I, right, is just the second derivative with respect to time of the position of the ith object, right? Well, you've got a sum, so now you've got another, you've got a derivative right here. That derivative is a linear operator. It's a fancy way to say I can pull it in and out of the summation sign. And what else? I also have a sum on m. Let's see. Well, there's a couple steps. You can follow it through and what the book goes through. I think in the interest of time, so we spend more time on basic concepts. I'll go ahead and skip to the chase and say that if you go through the various steps, the outline of the book, you find that, I'm just going to switch the net in total, doesn't really matter. This force can be thought of as ma, where this m is, again, my sum on all the individual masses, and this a is the acceleration, but not of any particular object. It's the acceleration of the center of mass. So this is just the second derivative with respect to time of the position. Oh yeah, just so you know, this is an operator acting on him. I can put him up here, so if you're more comfortable with that, either way is fine. Just notation. But this thing is the center of mass position. How do I find that? Right here. Right? So R sub cm just means this weighted average of locations. If you plug all this stuff in here, it turns out that this thing is the same as that. It's the same as that thing. It doesn't matter if the way you get it is by adding up the individual net forces of all n objects. You can skip that step. If you know you've got 3 pieces of chalk and you know where the center of mass of the chalk is, or if you don't, it's a true fact that the acceleration, the change in motion, right? The acceleration of the center of mass's location is related to the net force on all the objects summed up, with the proportionality being the mass of the whole system. So this is a huge simplification, right? I mean, so far in the class, we've pretty much been thinking about point-like objects that just exist in one place in space. But this is saying, well, we can still use a very simple single equation to describe the motion of very complex objects, right? Like my body, right? It's got lots of relatively moving parts, right? And there's mass over here, there's mass over here, it's extended. All we have to do is figure out where my center of mass is, and we know that the net force is on my body. So the net force, I should say, on my body. If you add up the normal force on the ground, gravity acting down on me, and something pushing on me from the side, there's a spring acting on different parts of my body. If we add all those forces up vectorially to get the net force in my body, the center of mass of my body has to obey this equation, right? But this is just my total mass. So we need to know how much mass is in my arm or my chest or whatever else. It's a really huge simplification. It's a really powerful idea. Okay, and we're going to find a similar thing for momentum and for kinetic energy, that the center of mass gives us a way to think about the whole system in a simple way with a single equation. It didn't have to be that way. It works out nicely because of the laws of physics have this nice property. So, and again, for continuous matter, we can take an integral instead of a sum for all these things. And so what does that mean? Just to make I'll make a simple idea here. Suppose I've got a distribution of mass like this. I've got a u, upside down u, right? So all this mass evenly distributed along this thing. Think about where the center of mass is. So is the center of mass going to be right inside the object up here? No. The center of mass, because what I do is I say, okay, I got mass over here and I got mass here, and I add up those locations and weight them. It's going to be somewhere, like I had a perfect circle, where would it be? Suppose I had a perfect ring. So I have a perfect ring of mass, and I weight the locations equally of all these places. Where's the center of mass going to be of this whatever it is, inner tube, whatever it is? It has to be right in the center. So for something like this, only half of the ring, it's not going to be at the center. That's where it would have been if there were mass down here. Not going to be up here. That's where it would be if this thing was straight, right? So it's somewhere in the middle. It's like down here somewhere. So the center of mass of an object that's bent like this is not inside the object, but it's also not maybe where it would have been if you had the object all the way down here. So that's somewhere in here. So if that makes sense to you, that's what's conveyed by these equations, right? That's what center of mass means. That's where it would be. But it's really useful for solving physics problems. So let's see that. Oh yeah. So here's two. So let's do this. Let's do so today I get to well, if we get far enough, we gotta know burn things and I draw pictures. It's a fun lecture for me. So all right. So here's a couple masses that are equal. These are two equal masses, right? And there's a spring between them. Let's assume it's an ideal spring that has zero mass. All right. And the spring, so let's see, you might think, well, there's 3 objects in the problem, there's a spring. It's massless, but nonetheless, it's going to interact with these things. It can exert a force, right? So what I'm trying to do right now is a situation up where I've got 2 objects of equal mass. They're initially at rest. I'm going to light a fire down here and burn a piece of rope or string that's holding the spring taut, right, together. It's coiled, right? It's going to uncoil the spring. The result is going to be that both these objects experience an equal but opposite force, right? We can use Newton's third law to think through, whatever force gets exerted on this guy, on this mass over here, it's going to point that way from the spring. Well, it exerts an equal and opposite force on the spring that way, right? And then over here, the same thing, back to back. And the system is closed. There's nothing else. Well, there's ropes suspending it. There's gravity acting on it. But those are in the vertical direction, right? So the ropes or strings are pulling up on the spring and on the 2 ropes, and force of gravity is pointing down. So there's no net external force acting on any of these objects right now. That's why they're not accelerating. When I light this up, then all of a sudden there's going to be some internal force. It's really important to keep these straight. Internal versus external. And an external force would be if I push with my hand being not part of this system. But there's going to be an internal force. So what's going to happen? These guys are going to be accelerated, right? They're going to fly out to the sides. But which one's going to go further? If they have equal mass and there's a spring between them and there's only internal forces, is one of these guys going to go further out than the other, or are they going to go out equally, or what's going to happen? Yes, equal. I think that's right. I think it'll be equal. So let's check it out. If I can get, let's see. I think I have to go this way first. Oh, yeah. Fire. All right. Like this. Oh, yes. There it was. I know you were waiting for the big bang there. Okay, so now let's do it over here. Now we've got 2 masses that are unequal. Big mass over here, little mass over here. What's going to happen? Who's going to go further? Little mass. Yes, I agree. Let's see, it's kind of humorous. Oh, yeah. He gets pushed around, right? This guy hardly moved at all. Now, in terms of their momenta, in terms of the momentum of each of these objects, right? Which one had a bigger momentum? And let's see, when I say bigger, I mean the magnitude. Momentum's a vector. This guy shot this way. So initially, right after the spring sprung, right, this guy went that way. His momentum pointed that way. Over time, it changed because it's a circular motion, right? But forget that. Initially, it's going that way, horizontal. Which one had a bigger momentum? The big guy or the little guy? Who thinks big guy? Little guy. Same. I think same as well. And those of you who didn't think that was different, you thought this one ended because the velocity was bigger. But remember, momentum cares about the mass, not just the velocity. And there's a linear, momentum is linear in mass and it's linear in velocity, right? Momentum is m times v. And if I'm talking about object I, then I'll say mass of I, velocity of I. Notice this is a function of time, meaning the velocity is changing with time. So I mean at some particular moment in time. Same for here, same for there. The mass isn't changing here. There are problems where the mass can change, like a rocket. I think I'll have an extra credit problem with a rocket on the homework, but I won't test you on problems. Well, is that true? You could have a problem on an exam where mass is changing, but it'll be changing very slowly, so that you can think of any moment in time as being a fixed quantity. But you won't have, in other words, well, we'll talk about this next week more, but when you've got momentum, so momentum can change rapidly if the mass changes rapidly. In fact, this is important for rockets. Rockets are full of fuel. That fuel is part of the mass of the rocket. To get the rocket off the ground, you got to accelerate this huge amount of mass of the fuel. But after a while, the rocket is lighter, right? Not only is it lighter, it's further from the Earth, 1/r². Well, you didn't read that chapter. But it's also the case that there's less mass. But we're not going to worry about that. We're just going to say this is a case where the masses are the same over time, but they're different from each other. So if I want to know which one's got a bigger velocity or smaller velocity, I'd say, oh, well, let's see, what happened? They initially were holding still. I lift this guy up. Well, let's do F equals ma. We can do it for the whole system. The initial acceleration was 0. Let's see, isn't it? There was no net external force. So that means the center of mass. What does that mean? The center of mass had what was the acceleration of the center of mass of the system consisting of both these objects and spring? Well, what's the net external force pointing in this direction? There's 0 external force. There were forces, but they were internal. And the reason we have to worry about internal for Newton's second law is they cancel out. Like this guy exerts a force on him going that way, but this guy exerts a force on him going that way. And this guy, and so on. The back-to-back forces cancel out. Don't bother with them on a free body diagram. So we've got this situation, right? And then we say, okay, this broke, and so now immediately after, the spring has imparted whatever it's going to do, it's exerted its force on these objects. You'd say, well, the center of mass, well, F net total, right, on the system was equal to 0. So that and that equals ma. So m times a. So the center of mass had to be 0 because capital M's not 0. These things have mass, so that would be 0. Well, if that's 0, it means the center of mass was initially holding still. At the end of the problem, it's still holding still, same location. That means that the momentum. So when I say so, yeah, this leads into momentum conservation. So momentum must be conserved. The center of mass didn't move. Why is that? So let's see. I'm doing this a little out of order than the way I intended, but we can just do it like this. All right, momentum. What is the momentum of the whole system? We'll call it capital P. Still a vector. We'll call it capital P to just indicate the whole system, right? What is that? Well, it's just the sum of all the constituent parts of each of their momentum. So little p, so I now, right? What is that? Well, it's just the sum, right? Equals 1 to n of mass of each of these guys times the velocity of each of these guys, right? I think I did that right. Yes. And this is for a given moment in time, right? Well, if we go through a whole bunch of algebra that I also skipped over here using the same tricks. Oh, sorry, I have to look around this thing. What do you get? You find that another way to think about the momentum of the total system, the momentum of the entire system, isn't thinking of just summing up individual momenta of each of the parts. You can also think of it as the total mass of the system times the velocity of the center mass. So again, I'm skipping the steps to get there. The book shows you these steps. It's the same kind of steps I skipped over here. It has to do with pulling things that are constant out of summation signs, and it's a little tedious, but it's the same basic ideas. And when the dust clears, you get this new result that says, there's 2 ways to think about the momentum of the whole system. I'll write it over here again in case people can't see past this thing. You can think of it as the sum over all the individual momentum of each of the parts, or you can think of it as not as a sum, just as a total mass of the system times the velocity. You need a vector here, right? Momentum's a vector of the center of mass of the system. Great. So center mass is really powerful. It says that if I want to know what my momentum is, I don't need to worry about adding up the individual momentum of all the parts of my body. If I know where the center of mass of my body is, and what its velocity is, and I know my total mass, then that's my total momentum right there. And what this tells us is that if there's no external force acting on the system, momentum of the system doesn't change, even if there's internal forces. So this was a case where there were internal forces, but there was no external force pointing in that direction. So that means momentum was conserved. And what was the momentum of the system before I lit the fire? It was 0, because nothing was moving. So therefore, the center of mass itself was not moving. So whatever, I didn't say what the mass of these objects is, but it has to be 0. And then after I light the fire and there's internal forces and these things fly apart, it's actually an example of what we'll call a collision, but it's sort of a collision in reverse. Usually we'll think of collisions where objects are moving and bump into each other. Collision. This was an example of a collision, if you like, where the objects started off together and then flew apart. But physicists think of it as a collision. So it's an example of an interaction. A collision you think of as an interaction that involves only internal forces, right? It wasn't an external force coming in on this system. There were internal forces that resulted in changing the velocities of individual parts of the system. But the center of mass of the system had the same momentum, or I should say, the system itself had the same momentum before and after. That means the velocity of the center of mass of the system didn't change. It was 0 at the start, it's 0 at the end. So if I want to know which one's going to move faster, and for that matter, which one's going to wind up going further or go higher up, what I have to do is just figure out, if the momentum is 0, that equals the total momentum of the system. What is that? That's whatever the mass of the little guy is. We'll call that little whatever, M1. We'll use M1 for the little guy. So here's M1, here's M2 for the big guy. So M1, V1, right? And I'll say X component. So let's just do X component, where X is pointing this way. Did I draw this correctly? Like I did. The little guy's on the left, big guy's on the right. Let's make X in the positive direction to the right, and say, the X component of the momentum at T, how much time? So let's call this T0. I drew this as if it's already broken apart. So there's a V, let's call it time 1. I'm doing retroactive corrections to my simple picture here. That's okay. So here's my V. Now I'm in trouble because I got zeros and ones. Let's do initial final. All right, so here's, let's do T final. And this is M2, it's M1. So if I say V1 final, I mean, and it's the X component, right, if you like. Then that's this guy's velocity. At final time, he's mass 1, it indicates it's him. This is V2 final. And maybe I'll look at the X, get rid of those up here, but we'll use them down here. Great, so that means I need this at time final. Oh my gosh. And I know people are dying. M2, V2, it's always a trade-off between clarity and keeping people awake with all the details. So yeah, mass 1, mass 2, V1, V2, that's right. And then make sure these are the same things. Here is this. If I want the X component of momentum, better have X components of these guys. If I want the final time, these both better be final. So good. We know that it's 0 here because if I write the same equation down for the initial case, well, this velocity and that velocity are both equal to 0 for initial. Add 0 and 0, you get 0. Momentum was conserved because there was no external force. That means that this whole thing has to equal 0, and therefore we know that this thing has to be equal and opposite to this. So if this guy has let's see, which one's on the right? Which of these guys has a positive X component to its velocity? M1 or M2? M2. So he has a negative. So this is negative, that's positive. And in particular, if we know suppose we knew what V2 was, we could isolate V1 and say, well, it's equal 0. I see V1 X final, right? That's just going to be it's going to be negative V2 X final times the ratio of the masses, right? So the bigger M2 is relative to M1, the bigger V1 is going to be relative to V2, right? Sort of common sense. And you all knew that. You knew what was going to happen. That's just formally how you calculate it. And we use their conservation of momentum. Now, when you write out conservation of momentum in general, you can do it the same way we do it for conservation of energy, right? So for conservation of momentum,